Hello and welcome to the next part of bipolar junction transistors. This is part two of a two-part lecture, two of two. Let's go ahead and move forward. All right, so let's talk about the basic collector curve, characteristic curve. What is it? So collector characteristic curves, they show how current through the collector I sub C changes with the collector emitter voltage, V sub CE. I don't know why I keep saying I had a problem with that. VCE, I sub C, V sub CE. It just sounds weird saying the whole thing. I'll just say VCE, and I'll say I sub C if it's two letters. Right, yeah, so with respect to VCE for different base currents, so I sub B. And these curves are essential for understanding how a BJT behaves in different operating conditions. So we have what's called, if you see here in the graph, the saturation region. This is the region where the transistor is fully on. The collector emitter voltage, VCE, is low, and the transistor allows maximum current to flow from the collector to emitter. The collector current, the I sub C, is high and relatively constant regardless of the increase in VCE. So any change in VCE is not going to cause any more change in I sub C. And the transistor acts like a closed switch. And how do we know this? So on the characteristic curve, that saturation region is where VCE is low and I sub C increases quickly as the VCE starts to increase. Right? So let's talk about the active region now, that middle portion. So this is the region where the transistor in its normal operating mode, it's amplifying signals, right? The base emitter junction is forward bias and the base collector junction is reverse bias. That collector current, I sub C, that's directly proportional to the base current. So right, any small change in base current gives you a large change in collector current. Oh, I hate when excuse me, I slouch and then it looks weird. Okay, can never center myself on this camera. Yeah, it's proportional. I sub B is proportional to I sub B. How do we identify that in the curve, right? The active region is where I sub C increases linearly with I sub B, and the collector emitter voltage VCE, right? That's moderately high. So it appears as a slope on the curve, and it shows I sub C versus VCE for different I sub B levels. I'll show you another graph that actually shows many different I sub B levels. During that breakdown region, that last part to the right, this is the region where the transistor is experiencing that breakdown due to high voltage collector emitter. That leads to excessive current flow and it actually damages the component if it's not controlled. So it leads to destruction of the component. Right? So how do we describe this behavior on the graph itself? Because we're looking at the curve itself. So VCE is very high. The transistor enters breakdown. The IC current, I sub C current, that increases sharply, and then the transistor can become damaged, right? If it's not designed to handle those large conditions or those conditions. So I'm recording, yes. That's it. Let's just move on to the next slide. Is it moving? Oh, yeah, I'm sorry. It has, I forgot this slide has these boxes. Here we go. So more about the general characteristics of the collector characteristic curve. So when you have breaking this down, when you have a set amount of base current, I sub B, you create curves. I'll show you again in a couple of slides what all the curves look like that show how the collector current I sub C changes with different collector emitter voltages. So we still have that cutoff region where VBE, voltage based emitter, is approximately 0. I don't know why my voice went up like that. Is approximately 0. And all this means is the base emitter voltage is very low, so the base current is almost 0. It never really is, but it almost is because we do have some leakage. The cutoff region, when the transistor is in this state, it's off and it doesn't allow, again, ideally any current to flow from the collector to the emitter. So we say I sub C is also approximately 0. I feel like my voice is inflecting up. Is also. All right. Then we get to the saturation region, right? That's when VBE is 0.7 volts and VCE is anywhere between 0.2 and 0.7 volts. And so that's when the transistor is fully on. It's the saturation region. The base to emitter junction and base to collector junction, those are forward biased, and that just means that the transistor allows that maximum amount of current to flow from the collector to emitter. And the current isn't affected much by changes in the base current anymore. Active region, this is again where VCE is 0.7, like I said in the previous. And it just means that the base collector junction is reverse biased. That's it. The transistor is amplifying when it's in the active region, so it's amplifying signals. The collector current, we say it's proportional to the base current. So an increase in base current, a tiny bit in base current is going to give you an amplified proportional increase in the collector current, and vice versa. When it decreases, it'll decrease. So the signal should follow and mimic the signal being put on the base. That's it. Let's keep going. Making some good time. All right. Continuing, we have the excuse me. The active region and the collector current. Let's talk about these two things. So when you have the base collector junction, the BC junction, and when it's a reverse bias, meaning it's not letting any current flow easily, not when it's not allowing any current to flow, because we do have some. That collector current I sub C, it stays steady for a given base current IB, right? I sub B. So even though the VCE, the voltage between that collector and emitter is increasing, the collector current doesn't change much. When you're in the breakdown region, right, so VCE becomes too high, the transistor enters that breakdown region. What this means is the reverse bias BC junction, it starts allowing too much current to flow. And again, we say this damages the transistor. So we're looking at the same thing, but from slightly different perspectives. So safe operation, you want to avoid that breakdown region. So you design your circuit to avoid that. Whenever it gets into that, it's probably because you have a fault in the circuit somewhere. Something else broke down. So you should never operate your transistor in that breakdown region because it'll just cause permanent damage, and it cascades. Even though you may be in that breakdown region for like a spike, some material does break down. So the next time it just breaks down faster and faster. So even if it's just some intermittent type of thing, it'll just cascade and break down faster in the long run. Yes. All right. So we said collector characteristic curves, plural. What are collector characteristic curves? And again, you see here in the graph, the curves show how the current through the collector, the I sub C, changes with collector emitter voltage, VCE, for different base currents, IB. Now you can generate this graph with a transistor if you have the right type of device. We used to have a transistor mapping device that would actually calculate these characteristic curves. You just stick the transistor in there into the circuit already built into the device, and it would run different base currents and give you the characteristic curves. Really, really cool. You can do this in the lab manually, so you'd basically be changing the circuit to vary the different base currents and sort of plot your collector currents and your VCE and so forth. But there are devices that do this automatically, and you get this in the spec sheet. So if you get a particular transistor, always look at the data sheet. Right? So looking at this sheet, what do we see? We've got the horizontal axis, which is the x-axis, the vertical axis, which is the y-axis. The x-axis shows the collector emitter voltage, VCE. The y-axis shows that collector current, right? So we have voltage to current here. Interesting. It's just a relationship between current to voltage to current. Not like what you're used to seeing, a time to some amplitude or, yeah. So when you're reading the curves, what you need to do first is find the base current. So you locate the base current you want to use, look for the curves that's labeled with the different base currents I sub B. So each curve shows how I sub C changes for that specific IB. So you'll be looking for the curve that you'll be using for your conditions. So look at the shape. They all look basically the same. You have that active region. The curve rate rises, then levels off. VCE is low. IC increases with VCE, but after that certain point, I sub C levels off, even when you have an increase in collector to emitter voltage. So that flat part of the curve, that's the active region. That's where the transistor amplifies signals. That's where you want to design the circuit to operate. Um, Looking at all these curves again, we can see the saturation region. You do the same thing. When VCE is very low, the transistor is in that saturation region. And this is where the transistor is just fully on. And so collector current is at its max is very, very high. It's relatively constant. Even if you change VCE a bit, it's not going to matter. And then that breakdown region, again, it's just, again, we're looking at multiple curves just on one graph, so don't see this too complex compared to the last graph we saw where it just had one specific curve for one specific I sub B. So again, when we're looking at the breakdown region, just to kind of repeat and recall and sort of re-emphasize, VCE gets too high, the curves show a sudden sharp increase in collector current. And then this breakdown region is where the transistor might get damaged, but it will get damaged. The book, they say might, but even if it's a small damage, like I said, where it leaves the region and it operates fine, you don't have to replace a component, in other words, but the next time it does that, it breaks down even faster and faster. So it does cause some like fatigue to the material. And so how do you use the curves when you want to design? You can use the curves to decide how the transistor is going to work in your circuit. So if you want the transistor to act as an amplifier, obviously you need it to be in that active region. So if you're troubleshooting a circuit with a transistor and your transistor isn't working as you expected it, assuming it was designed correctly, the circuit, you can look at these curves and that'll help you figure out if it's in the right region or if it's like the VCE is too high. So yeah, let's keep going. I want to continue with the cutoff region. Excuse me. I'm trying to go straight through these recordings so that I can make them short and you don't have to sit in front of a computer too long. Let's talk about the cutoff region. So I'm not pausing for yawns and stuff like that. I'm just going straight through. Cutoff region, right? So cutoff region, there's no base current. Approximately, right? I sub B is approximately 0. Well, let's say 0 just to make your understanding of it easier. The transistor is in the off operation, and it's in the cutoff region, right? The collector leakage current. So even though the transistor is off, we technically still have a small amount of current that flows from the collector, and we call that the collector leakage current. The value of the leakage current is usually very, very, very small, something in microamps, but you're going to see it there. Even on multisim on the simulator, it'll simulate some leakage current. So your software takes into account of what real components look like. But if you have no base current, the transistor technically is off and it allows only some tiny leakage current to flow through it. So it acts like a switch in this case, in the off position. When you forward bias the base to emitter junction, the base to emitter, remember where the arrow is pointing down, and I just use that one as an NPN, so if you can recall it. The base emitter junction is forward biased. That means you have base current flowing, and the collector current actually increases because that's flowing. So in that case, if you remember the formula, I sub C is equal to beta DC times I sub B, where beta is that measure of how much a transistor amplifies based on the base current. That's based on the manufacturing of the component. You'll find that in the data sheets. You can also calculate it if you didn't know it. Right? If you had a component, you pull it out of a drawer, you don't have the spec sheet for it, you don't know what the beta is, but you need to know what the beta is for design. You can do a couple of circuits, do some measurements, and calculate the beta so you can get an idea of what it is. There's some standard values for betas. So if you see it's close to a certain number, you can pretty much guess what it is. And actually, it might be good to actually calculate the exact beta. Hold on, I'm losing my center on the camera. That was I sub C. We said, now we talk about V sub CE and I sub C, right? So when the collector current increases, the collector emitter voltage drops, and that's because VCE is equal to VCC, the source voltage, minus the voltage drop across that collector resistor, which is I sub C times RC. So as that goes up, minus VCC, VCC actually drops, it gets smaller. And just remember, VCC is the supply voltage. That's what you supply, the battery or whatever you're doing to supply the amplifier. Then you get to that saturation point. So that's when the transistor's in saturation. So we say IC, the collector current stays relatively constant. So even if you increase the base current anymore, nothing's going to happen. It's in saturation, right? It can't increase any higher. So when we say VCE, voltage collector emitter at saturation, that means that the collector emitter voltage when the transistor is fully on, right? What is that voltage? And when we say I sub C under saturation, that's the maximum collector current when the transistor is in the saturation region. And you can get those from the graphs if you get the graph. So you get the graph that can tell you what to expect from the transistor. All right, let's keep going. All right, DC load line, right? So what is it? Well, it's just other than it's a straight line on the transistor's collector characteristic curves. What it does is it shows possible values of collector current and collector emitter voltage, so VCE. That's based on whatever external circuit, resistor, and supply voltage you design for the circuit. So if you want to learn how to use the graph, right? You want to say you want to draw the load line. You draw the load line by plotting the maximum and minimum points of IC, the I sub C current, collector current, and VCE as well, based on the circuit that you've designed. And so your load line is going to be specific to your load line, and obviously the components that you have on your circuit will determine all that. Everything's still the same because KVL still KVL, KCL still KCL, but VCE is going to be VCC, the source voltage, minus the voltage drop across that resistor, or I sub C times R sub C, right? That doesn't change. And remember again, VCC is just that supply voltage, whatever the supply voltage is, 12 volts, 15 volts. R sub C is that resistor on the collector. You can determine the cutoff point. So when the transistor is in the cutoff region, you can assume that IC is 0 or something extremely close to 0. We say it's negligible, so we can use 0 to make it simple. And that's the point where the load line intersects the VCE axis, and we call that the cutoff point. And so that shows that maximum VCE. We can also determine the saturation point. So this is when the transistor is in saturation. Remember we said I sub C is at its maximum for some given value of beta current, I sub B, right? Base current, I said beta current, I meant base current. I got confused with the beta earlier. Yeah, so with any given base current, I sub C is not going to change anymore. It's a saturation. So that's the point where the load line intersects I sub C axis, and that's called the saturation point, the maximum I sub C. And that's how you utilize the DC load line, drawing the DC load line, and utilize the graph for looking at characteristics for your circuit, and it's particular to your circuit. All right, so let's go ahead and look at this example. We are in slide 9. I got to make this bigger because I can't see the images. I can see the text. So when is the saturation current and the cutoff voltage for the circuit? Assume VCE is 0.2 volts in saturation. Is a transistor saturated? So luckily they calculate this for us. So according to the formula, go back to the previous slide, saturation current, when you plug it in, VCC 15 volts should be right over here, right? Sometimes it's drawn up at the top. You'll put 15 volts going down to RC and then the transistor. It's the same thing. Having the voltage over here and then having that volt. Oh, you can't see my mouse. Shoot. Okay, right there. Yeah. So this is VCC. I was just saying that sometimes VCC, well, actually most of the time, it's drawn up here on top. Again, still with the positive to the collector. And then it's assumed that you understand that it's the other side's the ground, which is connected to this side. So when it's drawn here like this, it's just kind of easier to see that you have a positive voltage on the collector, and then the negative side of the battery is to ground, which is on the emitter, making the ground more negative, right? Anyway, saturation current is going to be according to this specific component and this specific transistor beta. So the beta for this transistor is 200. It's going to be 4.48 milliamps. That's the saturation current, or the current at saturation. VCO, which is the output, should be VCC, which is 15 volts, right? And then, because in this case we have no input signal. And then IB, the base current, is going to be, this is the voltage applied at the base, minus 0.7 volts. 0.7 volts is a volt across that base to emitter junction. Remember, we have to forward bias that junction to get this thing to actually work. And so in our calculation, we're going to determine what base current we need on there to get this to work. So it's 3 volts minus 0.7 volts. That's that voltage difference across that base resistor. 3 volts on this side, 0.7 volts on this side, divided by the 220. And that's going to give me the current that's going into the base. Oh, I don't know. I keep slouching. All right. But I'm also trying to see the slide because it's so small. Oh, then I sub C, you can calculate that using beta. Again, this is a beta of 200. Beta times IB, 200 times 10.45 milliamps is 2.09 milliamps for I sub C. Yeah, I can already see, if you haven't caught it, a typo. It's 10.45 microamps. This should be 10.45 micro, not milli. But the calculation works out the same. 10.45 micro times 200 should give me 2 milliamps. So if you're actually listening to the lecture, this should be micro, like the way it is up here. If you're not listening to the lecture and then you ask me a question in class, why is this not coming out right? It's not because you didn't listen to the lecture. All right, and again, the saturation current through the collector, when it's less than, when the current to the collector is less than the saturation current, so whatever that maximum is, it's just saying your transistor is not in the saturated region. Right? So it's still going to be in the active region where it can amplify. All right, key terms that you need to know for BJT amplifiers. So those that are highlighted and underlined. Linearly, BJT is a current controlled device, base emitter, remember base emitter, forward bias, base collector, reverse bias, and just remember that. So what is an BJT used for? For linear amplification, right? So we always operate this in the linear portion. According to the curve that we saw earlier, we always want an expected linear output for some input. We never want to have something operate in a non-linear region. We do stuff like that as well, but only when we absolutely have to. But this particular component has a nice linear region where we can actually work with, so that you will get a very steady and predictable output. It's not that you couldn't get a very steady, I shouldn't say you can't do that, but in non-linear regions, it's just a little more unpredictable, right? So, and you have to be a little more tight with your controls and your feedback. All right, BJT amplifier. So here's a BJT amplifier. It says as an input capacitor, which is used to remove any ripples from the AC source. So we have an alternating current running here. We have a direct battery source being applied to the base to actually bias this circuit to make sure that this is greater than 0.7 volts so that we can actually get this thing in the active region. But we also have this capacitor here because this circuit, the signal may have a lot of noise and ripples. So what this is going to do is just reduce that ripple. All right. And so it's just meant to make the input a little bit smoother. This AC base current produces much larger AC collector current. So notice that we have this tiny base current here provided by this source. And then on the collector side up here, the current flowing from collector to emitter, or electrons flowing from emitter to collector, that is going to be much larger because our voltage on VCC is much larger than any output voltage. So this VCC is always going to be something like 12 volts, 15 volts, something much, much larger. The signals that we're trying to amplify is something very, very tiny, something in the millivolts. Um, and so what we're trying to do is get a directly proportional replication of that little input signal, amplified. So that little signal there should just be amplified. We're not changing the frequency. We're not changing any other characteristics of the signal. We just want it bigger. Amplitude. All right. BJT as a switch. Oh, we're doing really good on time. BJT can be used as a switching device in logic circuits to turn on or off current to a load. And so as a switch, the transistor is normally in either cutoff, which the load is off, or saturation, which the load is on. Sorry that my face is covering that part of the circuit down there at the bottom, but you can see what it looks like here. So in cutoff, the transistor looks like an open switch. So when you have no current to the base, it's going to act like it's open. So you got no current flowing here. All right, so this is like an open switch. When it's in saturation, you got this forward bias and you have current flowing from that collector to the emitter, so it looks like the switch is closed. If I wanted to turn something on, I would put it on this branch, right? Let's say put it right there on the emitter. Let's say I have an LED that needs to turn on when I'm indicating that something is something happening, right? And that's proportional to some current that I'm reading off the circuit. If nothing's happening and this thing's not on, I'm not going to get any current, so that LED will like never turn on. But once that fault or whatever it is that it detects or it senses allows this base to emitter current to voltage to overcome the biasing, current flows, and if I had an LED right there, that would light up. And so it acts like a switch. It turns the LED on or off. Right. It could be anything else. It doesn't have to be an LED. It could be a relay for a fan, and you could be measuring temperature or pressure or whatever it is. Um, but you have to design a circuit so that in one condition, the off does one thing and the on does something else. All right. 13. For a BJT to act as a switch, here are the formulas. The VCE cutoff is going to be equal to VCC. Saturation current is the difference between VCC and VCE at saturation divided by that collector resistor. And then the, keep wanting to say beta, the base current is going to be equal to the IC current at saturation divided by the beta of the transistor. Beta of the transistor is normally given to you. It'll be given to you in the problem. Or again, if you know the part number for the transistor, you can look up the data sheet for it. And if they don't give it to you in the problem, they might expect you to calculate it. They're going to give you other information. Um, so in other words, they may give you saturation current and you solve for beta current, and then you can use that to solve for BDC. Or they might make you run through a few steps. All right, the last slide we're going to talk about is phototransistors. We talked about photodiodes, if you remember that. Did we? Yeah, special kind of diodes. Phototransistors, basically the same thing. So when light hits that photosensitive base of the phototransistor, it creates a small base current. So it's highly sensitive. Phototransistors, they're very good at detecting light. They have a high gain. This means that they can amplify the smallest current caused by light. So don't quote me on this, but the night vision goggles, they probably use some type of phototransistor to amplify any kind of light that's in the area to light up the display, so you can see something in the lowest light divisions, lowest light conditions. All right, so you can use these. Besides that, and again, I'm just speculating on that one. You can use them in devices like light-operated relays or optocouplers. Am I still slouching? Yeah. Okay. That's it. Okay, and that is the last slide. If I click, it's going to end the recording. I want to say thank you very much for your time, and watch these recordings as before you do your reviews and labs and quizzes. It shouldn't take that long. Doing a recording, I think I did all this in about an hour and a half versus the 5 hours that we normally take for lectures. All right. Thank you.